Hi, this video is more about standing waves, but in this case, they're about standing waves in air columns, columns of air. So standing waves can form on strings, and they can form in columns of air. And this is how many wind instruments produce musical notes. So let's begin with a pipe that's open on both ends. An example of that would be a flute, because you blow across one end and it's open on the other, or perhaps literally open pipes like you find in wind chimes. That would be this kind of situation. So standing waves form when a wave interferes constructively with its own reflection. And so sometimes it's difficult for students to grasp the idea that a sound wave can reflect off the open end of a pipe, because what's it reflecting off? But remember, there's a pressure difference between inside the pipe and outside the pipe. And so that large change in pressure difference from inside to outside acts like a barrier. And so the wave can literally reflect off that pressure difference. And so the simple act of putting the sound wave in the pipe and then having it go through and there's the open end, that constitutes a big change in pressure. And so it can reflect off that pressure difference. Now, the simplest pattern that would fit in a pipe that's open on both ends would be this one. And you remember before that these kind of clam-shaped things that I have here, those are called antinodes. And in this case, we have kind of two half antinodes. And one whole clam is half a wavelength. And two half antinodes make a whole clam, which is half a wavelength. So here we have a high pressure, low pressure, low pressure. So the beginning of a low pressure, a high pressure, and the beginning of a low pressure. So this particular pattern here corresponds to the length of the pipe equals 1/2 the wavelength. The next simplest one that fits is this one, which is 2 halves. So that's 1/2 and a quarter, which makes 1 or 2 halves. Here we have 2 clams, 2 antinodes, which is a whole wavelength. And then we have a quarter. So that's 1.5 or 3 halves. And here we have 1, 2, 3 clams, which is 1.5 wavelengths, and another quarter, which makes 4 halves wavelengths. This is the same pattern that we saw on standing waves on strings. 1/2 lambda, 2 halves lambda, 3 halves lambda, 4 halves lambda. And without going through the extra steps there, let's just summarize that by saying this. For a pipe open at both ends, the frequencies that form standing waves are given by this equation. Now that's the same equation that we had for strings that are fixed on both ends. So this should already be, you should write it down in your notes, but it should already be on your equation card. Just make a note on your equation card that this equation works for strings fixed at both ends and for open pipes, for pipes that are open on both ends. And I already talked about flutes and wind chimes being good examples. So this equation, just write it down again in your notes for pipes open on both ends, but it also works with strings that are fixed on both ends. Okay, what about a pipe that's closed on one end, but open on the other? So in this situation, we have a bit of a difference. So on the closed end, you'll notice that we've got this high pressure region. And on the open end, we have a low pressure. So the simplest pattern that can fit on a pipe closed at one end is different. We have high and then the beginning of a low. This is half of an antinode, which is a quarter of a wavelength. So L equals 1/4 lambda. The next simplest pattern that can fit, high pressure, beginning of a low, is this one. We have a whole antinode, which is half a wavelength, and a quarter of a wavelength, which is 3/4 of a wavelength. And then the next pattern gives us 5/4. And the next pattern, 7/4. You'll notice here that the pattern is different. It goes not by 1/2, 2/2, 3/2. It goes 1/4, 3/4, 5/4, 7/4, and so on. So it's a bit different. If we did the analysis again, like we've done previously, we would find that for a pipe closed on one end, the frequencies that form standing waves are given by this equation. So this is a bit different. It says F equals NV over 4L, not 2L, but 4L. And now the N is an odd positive integer. So not all of the integers, just the odd ones, just the odd positive ones. 1, 3, 5, 7, 9, and so on. Examples of things that are pipes that are closed at one end would be like a trombone. Your mouth closes one end of the pipe, and then you extend the length of the trombone to make a lower note, or you pull the trombone slide in to make a higher pitch note. Trumpets, clarinets, saxophones, or even blowing across the top of an empty bottle. The bottom is closed, the top is open. There we go. And so you get a note like that. So let's do an example with this one here on the next slide. Let's say that we have a bottle, like the one I just used, and you blow air across the top, and it's 22 centimeters long. That's how tall the bottle is. What's the frequency of the loudest note you hear? Of the loudest note you hear. Now when you look at that question, you're only given one number. And so it looks like you don't have a lot of information, but really we do. Let's make a list of givens and unknowns. So I'm given that the length of the bottle is 22 centimeters, which I converted to meters, 0.22 meters. And I'm looking for the frequency, right? That's what I'm looking for. But it says I want the loudest note. And remember, the loudest note is almost always corresponds to the fundamental or the first harmonic note. So because that loudest note phrase is there, I know that n equals 1. And I also know the speed, because this is a sound wave, right? That's what I'm going to be hearing it with. So this is not the speed of the wave on a string, this is the speed of the wave in air. So this would be the speed of sound in air, room temperature we'll assume, unless we're told otherwise. So we actually know that the speed of sound is 343 meters per second. That should be on your card as well. So we actually know three things: the speed, the harmonic number, and the length. And then we're looking for the frequency. So the equation is what we want from the previous slide. I want to use the one for a closed pipe. It's closed on one end because the bottle is closed on one end. And so that's NV over 4L, where n is an odd positive integer. And then I'll substitute my values in. So n is 1, V is 343, and L is 0.22. Math, solve. Right, I got 389.77 hertz, and so that rounds maybe to 390 hertz at the bottom. Okay, thanks for watching.